Hello and welcome to the first entry of Mathias' Rust Corner. Did you know that the order of fields in your Rust Struct Memory Layout is undefined? In this video, we will take a look at some peculiarities with struct memory layouts in Rust. We will also discuss how it relates to drop order of struct fields, and how we can gain full control over both layout and drop order. First, let's take a look at the simple struct definition. Our struct foo contains three fields, a bool, an F64, and a U8 in order. With a default Repr Rust memory layout, fields are padded left to fit their alignment. Additionally, the alignment of a struct is the alignment of its largest field, unless this is overridden by the Repr align n annotation. But let's inspect the actual memory layout of the foo struct. The following program's output may seem odd at first glance. We use the std-mem offset of macro to determine the number of bytes a given field is offset relative to the beginning of the struct's layout. Notice how the compiler completely reordered the fields in our struct. The fact is, field order for the default Rust representation of structs is undefined. Let's explain why it's useful to allow the compiler to reorder fields on a typical x86 target. Consider how the foo struct will be laid out in memory if field order is preserved after alignment. The first bool has a size of 1 and is put at offset 0. The next type, F64, has an alignment of 8 bytes, so we need to add 7 padding bytes to fit it. This leaves us with a U8 at the end, taking up 1 byte. But, since the struct is aligned to the largest of its fields, we need to add 7 additional trailing bytes, leaving us with a struct size of 24. If, however, the compiler is allowed to rearrange the fields to optimize padding, we can save quite a bit of memory. We then end up with placing the F64 upfront at the offset 0. We can then add the U8 and finally the bool without any padding between them, since both of them have an alignment of 1 byte, leaving us with 6 bytes of alignment padding at the end. This reordered struct has a size of only 16 bytes, saving 8 bytes per instance. Looking at those two struct layouts side by side clearly visualizes why layout order matters. It also highlights why it's nice that the Rust compiler does this optimization for us, since doing this by hand is tedious and non-trivial. Obviously, real C programmers would normally do this layout in a heartbeat. If you need to control the memory layout of a struct, you should use the Repr C annotation to force a C-compatible memory layout of your struct. The resulting layout will still abide to the alignment rules of your target, but the compiler cannot reorder fields. The primary use case for Repr C is when interacting with C or C++ code via FFI, or when receiving binary payloads over the network. For most applications, though, it is better to use the default representation and leave the layout optimization to the Rust compiler. Here, we can see the size difference between the Repr Rust and Repr C layouts of these two structs. But there is a complication. Since Rust determines drop order based on the textual order of declarations in our structs, we cannot always freely reorder fields in our struct declarations. This might lead to unfortunate trade-off situations between memory footprint and behavior. Consider this nasty unsafe program. The owner struct holds the resource on the heap, as well as a child field that has a pointer to the own data. The child struct calls report on the resource when dropped. In this version of the program, everything is fine. The child gets dropped before the resource, as per the order of declaration, and reports 666. But look what happens if we change the order of our fields. We end up dropping the box, freeing the memory on the heap, before we call report. And then our report prints random garbage. Which, in fact, means we are accessing memory we really shouldn't be accessing, violating all kinds of safety constraints that Rust wants to enforce. If you need to control both memory layout and drop order, we can use ManuallyDrop to get control over when we drop fields. As the name suggests, a field with the wrapper type ManuallyDrop will not have its drop function called automatically. Instead, we take the responsibility of invoking drop at the correct time ourselves. In this version of the code, notice how we explicitly drop the child from the struct's drop implementation. Since the struct's drop is guaranteed to run before the fields are dropped, we are able to enforce both memory layout and drop order for our struct. To wrap it up, it's important not to rely on the memory layout of Rust structs using the default Rust representation. If your application needs to have a specific order of fields, use #Repr C, and this is mostly useful when talking to external systems or over FFI. When using Repr C, make sure you understand all invariants involved in the drop order, otherwise you can get into serious trouble. That's all for this video. Make sure to subscribe to get notifications about subsequent Rust videos. Goodbye!